Acids and bases are important to understanding organic chemistry. At one time, chemists tasted compounds and used the sense of taste to characterize the substances. And so that's where, of course, acid comes from the Latin of acidus, meaning sour. And they would taste those substances and see that they were sour. And, I bet you can name a number of sour substances, such as citric acid in lemons or other citric products, or also in sour candies, acetic acid in vinegar, stomach acid, which is hydrochloric acid. Bases, or alkaline compounds, neutralize acids and are often bitter in taste. Lye, drain cleaner, baking soda, they're all common bases. There are several definitions for acids and bases. We will not focus on the Arrhenius definition, as it concerns acids in water, and we do not work typically in an aqueous environment in organic chemistry. So the first definition we will use is the Bronsted-Lowry definition. According to Bronsted-Lowry, an acid is a species that donates or loses a proton, whereas a base is a substance that accepts a proton. And recall that a proton is H+, and recall that a hydrogen atom, if you have a hydrogen atom, it has 1 proton, 0 neutrons, and 1 electron. So therefore, if it loses that electron to become H+, all that's really in there is a proton. So that's why it is sometimes referred to as a proton. So in the example below, we can see that we have hydrochloric acid reacting with water, and we can see that the red hydrogen that's illustrated is going to be lost from the hydrochloric acid, and it's going to be gained by the base, making therefore the hydrochloric acid the proton donor and the base the proton acceptor. Now in organic chemistry, we're going to frequently use our curved arrow approach that we've talked about before. So we could show the pair of electrons on the oxygen of the water forming a bond with the hydrogen in the hydrochloric acid, and of course the bond that was between the hydrogen and the chlorine would break, pushing those electrons onto the chlorine. And so this transfer of protons is referred to as an acid-base reaction. And we could see that this reaction is reversible. So if we were to look in the reverse direction, we could have the chlorine, or the chloride now, the chloride ion, serving as a base. And we would refer to it generally as the conjugate base since it's on the product side. And the pair of electrons in that bond between the hydrogen and oxygen would go back on to the oxygen. And so that the hydronium ion would be the conjugate acid, as it is a proton donor. As I just mentioned a moment ago, these reactions are reversible, and so therefore the conjugate acid is on the product side that it's formed from the conjugate base. So the conjugate acid results when a base accepts a proton, and a conjugate base is the result when an acid gives up a proton. And so we've already looked at the arrow pushing for the hydrochloric acid. We could look at that for the alkoxide ion reacting with water, and that would be the arrows for that forward reaction. And again, I've been showing you the curved arrows in these reactions, but just want to reiterate again that you could in a sense say that the base is attacking the acid. You cannot say that the acid is attacking the base. That just would not make any sense. So the acid really is not going to lose its proton without the base taking it. And so we can see also that this is always going to be a simultaneous movement of those electrons, or what we also sometimes call concerted, that it's occurring in a single step. So let's try a sample problem. So the first step that you need to do in trying to write a mechanism is you need to write the structures of the molecules involved, or the species involved. So the first species is KOH, and hopefully you remember from general chemistry that that is an ionic species in which you have an ionic bond between a potassium ion and a hydroxide ion. And if we complete the structure, we would think about the fact that that oxygen has 3 lone pairs on it. And nitric acid, of course, hopefully you can either recall its structure or, if need be, go back to the principles that we looked at in chapter 1 and draw a Lewis structure for this species. But right now I'm just going to draw out the species because we've already covered how to draw the structures in earlier chapters. All right, so what we can look at, of course, if we're looking at Bronsted-Lowry principles, the OH here, the potassium is associated with that OH because they are both charged species. It's an ionic bond, but the potassium is not going to play any role. It is going to be a spectator ion, and the hydroxide could potentially donate a proton. But because it already has a negative charge, donating a proton would simply increase its negative charge. So more likely, it's going to act as a proton acceptor or a base. Now, the nitric acid, of course, could have a part where it has this negatively charged species here that could act to accept a proton, or it has this proton that can be donated. And so technically one could originally think that maybe it could act as both. However, of course, this negative charge is offset by this positive charge here. So more than likely, it's going to act as a proton donor. And so therefore then, we could draw a mechanism in which this is going to be our base, this is going to be our acid, donating the proton, and we would form water and nitrate. And if we were to think about it in the reverse, the water could, of course, donate a proton, and so therefore would be our conjugate acid. And it, of course, came from our base of the hydroxide. The nitric acid is our acid, and the nitrate is now our conjugate base. So oftentimes we need to think about how a reaction progresses. Will it lie towards the reactant side, or will it lie towards the product side? And so for an acid-base reaction, we would want to consider acidity and basicity. So acidity is going to be the measure of the tendency of a compound to lose a proton, and basicity would be the tendency to accept a proton. And so it's basically, a measure of compounds' affinity for a proton. So therefore, a strong acid would have a strong tendency to lose that proton. So it would have a strong tendency to, in a sense, lose that proton and form its conjugate base. A weak acid would have very little tendency to do that, and therefore would lie more towards the HA. In this course, we're going to use both quantitative strength analysis, looking at numbers, so looking at pKa values, as well as qualitative, looking at the properties of the molecules, the structure, and how that influences its acidity or basicity. Recall from general chemistry that many reactions are at equilibria, and that we use equilibria constants to define or describe the equilibria. So we can look at an example with acetic acid and its dissociation in water. When a strong acid is dissolved in water, almost all of the molecules dissociate into the conjugate base and the hydronium ion. Therefore, the equilibrium would lie to the right, favoring the products. When a weaker acid, such as acetic acid shown on this slide, is dissolved in water, very few molecules dissociate, and the equilibrium actually lies to the left, favoring the reactants. And the degree to which an acid dissociates is indicated by the acid dissociation constant, or Ka, or of course is related again to the equilibrium constant. And if you remember from general chemistry that equilibrium constants are the ratio of the concentration of the products divided by or over the concentration of the reactants. And recall, of course, that these brackets that you see here are referring to concentration in moles per liter, or molarity. Water is not included in the Ka because it is assumed that the concentration of a pure liquid or solid does not impact the equilibrium constant. Now, that's not entirely true, and there is a concept related to activities that will be covered in analytical or physical chemistry, but it's out of the scope of organic chemistry. So for our purposes, therefore, then we can again look at this equilibrium and say it's related to the concentration of the acetate ion, the conjugate base, times the concentration of hydronium ion over the concentration of acetic acid. As you know from general chemistry, Ka values are frequently some number times 10 to a negative exponent. And just like the pH scale was developed to more conveniently deal with non-exponential numbers, we will use the pKa scale in organic chemistry instead of Ka. So much like pH is the negative log of the concentration of hydronium ion, or pOH is the negative log of the concentration of hydroxide ion, pKa is the negative log of Ka. So therefore you can see the relationship there. And the stronger an acid, so strong acids will have large Ka values, and they will have very small pKa values. Here's a sample of some organic compounds that we're going to encounter in this course. Very strong acids are going to have a pKa less than 1, so we can see those here. They all have actually a negative pKa value. So, but if it's less than 1, it's going to be very strong. Moderately strong acids will be between a pKa of 1 to 3, and then weak acids are 3 to 5. Very weak acids are 5 to 15. So this would be weak. This would be very strong. These are then going to be extremely weak, the ones that are left over here, because they are less than 15. We can use pKa values to compare the strengths of bases as well as acids, because if you have a very strong acid, its conjugate base, so that's how this table is set up, is going to be extremely weak. So the stronger the acid, the weaker its conjugate base. And of course, remember from general chemistry, you may have talked about that pKa plus pKb equals 14, or pKw, the negative log of the equilibrium constant for the autoionization of water. So how would we use these numbers to analyze equilibria? So for example, here we have an equilibrium reaction. If you want to review your mechanisms again, we could show that we have the hydroxide ion accepting the proton from the acetic acid and pushing a pair of electrons onto that oxygen to form the conjugate base. So we could look up pKa values. So acetic acid has a pKa value of 4.75. Water has a pKa value of 15.7. And as I mentioned before, the smaller the pKa value, the stronger the acid. So in terms of the strength of the acids, acetic acid is stronger than water. And an equilibrium is going to, basically you're going to always have the stronger acid plus the stronger base, and it doesn't have to be a strong acid, but a stronger forming the weaker acid and weaker base. And so that's why, since we see that acetic acid is stronger than water, that's why you can notice that it's going to favor the forward direction, that there's more of an equilibrium in the forward direction than there is in the reverse direction. And the other conclusion then we can make is that therefore OH is going to be a stronger base than acetate. And this is the acetate ion here. All right, so let's consider another problem. So they're telling us that the pKa of aniline ion, which is not shown on the slide, but you're given a figure, so that's C6H5, typically ends up being an aromatic ring. Remember that from your functional group. And we have NH3, and we would have the positive charge on the nitrogen. And so this has a pKa of 4.6. And we can see that we have methylamine. So this is methylamine. And we can see that the conjugate acid has a pKa of 10.6. So we would know that, of course, the aniline ion is an acid, and its conjugate base would be aniline. So this is aniline here. And so we can make predictions that the aniline ion is a stronger acid than the methyl ammonium ion. And why am I making that conclusion? Because we were told that this has a pKa of 4.6 and this has a pKa of 10.6. And therefore, remember, the smaller the pKa, the stronger the acid. And therefore, recall then that the base strength is kind of opposite of that. So therefore, if aniline ion is stronger, then aniline must be a weaker base than methylamine. All right, and so in terms of answering that question, then the question is weaker. Another thing just to look at on this slide really quickly is let's just consider the reaction that's given on the slide with the methylamine and why the equilibrium is written the way it is. If you recall from the last slide a moment ago, that water has a pKa of 15.7 and the methylammonium ion has a pKa of 10.6. So this is a stronger acid than water, and therefore the equilibrium would lie towards the reactant side.